Richard Feynman explains the big misconception about electricity. Let me tell you something uncomfortable. You've been lied to about electricity, not by bad teachers, not by lazy textbooks, but by explanations that sound simple and feel safe. And comfort, my friend, is the most dangerous thing in learning. You think electricity flows like water. You imagine little particles running through wires, delivering energy from one place to another. You nod your head and say, yes, that makes sense. But it doesn't. It only feels right because no one ever stopped you and said, wait, what does flow actually mean? In business, I learned this. When everyone agrees too quickly, something important is being ignored. Physics is no different. The truth is, if electricity worked the way most people believe, your phone wouldn't charge, your lights wouldn't turn on, and power grids would collapse instantly. Yet here we are, surrounded by electricity while barely understanding what it really is. And that should scare you, because electricity is not moving the way you think. Energy is not traveling the way you imagine. And the wire you trust every day is doing something far stranger than your mind has been taught to accept. So today, forget what you think you know, because the biggest misconception about electricity is believing you already understand it. Let's begin by admitting something most people are uncomfortable admitting. We don't really know what electricity is in the way we know what a chair is, or a dog, or even heat. What we have instead are models, pictures in our heads that help us calculate what will happen next. And the moment you confuse the picture with reality, you get into trouble. The most common picture people are taught is this. Electricity flows through a wire like water through a pipe. Now, that picture is not useless. It helps you solve homework problems. It helps engineers design circuits. But the problem starts when people believe that the picture is the thing itself. So let's carefully pull this apart. The flow idea sounds reasonable until you think, when you flip a light switch in your room, the light turns on almost instantly. Not after a second, not after a minute, instantly. Now, pause. If electricity were something that flows from the power station to your house, then it would have to travel all that distance first. Power plants can be many kilometers away. Even if electricity moved very fast, say close to the speed of light, there should still be a noticeable delay. But there isn't. So already, our simple flowing stuff picture is suspicious. What is actually moving in a wire? People often say electrons move through the wire. That's true, but also misleading. Yes, electrons do drift, but they move extremely slowly. In many household circuits, the average drift speed of electrons is slower than a snail. And yet, the light turns on immediately. So here's the puzzle. Electrons move very slowly. The effect of electricity appears almost instantly. So whatever electricity does, it cannot be explained by imagining electrons racing through wires, carrying energy like delivery trucks. That's the first crack in the story. A better question. What happens when you close a circuit? Instead of asking what flows, ask a more useful question. What changes when I close the switch? The answer is, the electric field changes. When you connect a battery to a wire, you don't send electrons on a journey. You create a condition, an electric field that already exists throughout the circuit almost at once. Think of it like this. If I push on one end of a long stick, the other end moves almost immediately, not because atoms traveled from my hand to the far end, but because forces were transmitted through the structure. Electricity works more like that than like water in a pipe. Energy does not travel inside the wire the way you think. Here's the part that surprises almost everyone. The energy in an electric circuit does not mainly travel inside the wire. It travels in the space around the wire. That sounds strange, but it's true. The wire's job is not to carry energy like a pipe. The wire's job is to guide the electric and magnetic fields so the energy moves where we want it to go. The fields exist in space. The wire simply shapes them. This is why insulation matters. This is why the arrangement of wires matters. And this is why imagining electricity as stuff inside copper gives you the wrong intuition. Why the water analogy refuses to die. People love the water analogy because it feels familiar. Water flows. Pipes carry it. Pressure pushes it. But electricity isn't a substance like water. It doesn't pile up in corners. It doesn't slosh. It doesn't spill. Electric current is a rate of charge movement, not a thing. It's like saying, how fast are people walking past this door? That's not a substance. It's a description of activity. And energy? That's even trickier. Energy isn't a thing either. It's a number we calculate to keep track of changes. So when people say energy flows through the wire, they are already compressing several ideas into one sentence and losing accuracy in the process. Why batteries confuse everyone? A battery does not store electricity. It stores chemical energy. When you connect a battery to a circuit, the battery creates an electric field that causes charges in the wire to rearrange themselves. That rearrangement happens very fast again, not because electrons sprint, but because forces propagate. The battery doesn't push electrons like a pump pushes water. It sets up conditions under which the system rearranges itself. That's a very different way of thinking. Why misconceptions don't actually break devices? Now you might ask, if people misunderstand electricity so badly, why does everything still work? Because you don't need perfect understanding to make useful predictions. You can design bridges without understanding atoms. You can cook without knowing chemistry. And you can use simplified electrical models without knowing the full field theory. The danger is not in using approximations. The danger is in believing approximations are reality. That's when curiosity dies. The real lesson, and this matters beyond physics. Electricity teaches us something important about learning itself. When an explanation feels too comfortable, too familiar, too obvious, that's usually the signal to slow down. Nature is not obligated to make sense to our intuitions. Nature only follows its own rules. Our job is not to feel smart. Our job is to ask better questions. And the biggest misconception about electricity isn't about wires or electrons or energy. It's the belief that understanding means having a neat picture in your head, when real understanding often means being comfortable with a picture that feels strange. Let's continue. But now we have to abandon an idea that people are very attached to. The idea is this, that you can understand electricity by looking at a single point in a circuit. You can't. Electricity is not a local story. It is a whole system phenomenon, and that's where most confusion comes from. Why looking inside the wire fails. Suppose you zoom in on a tiny section of wire, just a millimeter long. You look at the electrons there and ask, what are they doing? They're jiggling around. They're colliding with atoms. They're drifting slowly. From that tiny picture alone, you cannot tell whether the circuit is on or off, the bulb is bright or dim, the battery is strong or weak. That should already tell you something important. If the essential behavior of electricity were happening right there, locally, you'd be able to understand the whole thing by looking closely enough. But you can't. Circuits do not work piece by piece. A circuit is not like a line of people passing buckets of water. It's more like a stretched net. When you change one part, the whole thing responds. This is why breaking a wire anywhere stops the entire current, not slows it down, but stops it completely. The system only works when it is complete. This alone tells us electricity is not something traveling from point A to point B step by step. It's something that exists only when the conditions of the entire circuit are satisfied. Fields are not optional. They are the story. At this point, we must talk seriously about electric fields. Many people treat electric fields as a mathematical trick, something you use to calculate forces and then forget. But the electric field is not bookkeeping. It is the physical reality of electricity. When you connect a battery to a circuit, the battery rearranges charges on the surface of the wires. That rearrangement sets up an electric field everywhere in the circuit, almost simultaneously. And that field tells every electron what to do. Electrons don't decide to move. They respond. Why electrons are bad messengers for understanding? Electrons are tempting to focus on because they're tangible. You can imagine them as little balls, but they are terrible storytellers. They move slowly. They bounce around. They don't carry energy neatly from place to place. They mostly just get in the way. The important action, the energy transfer, is happening in the electromagnetic field. That's why when engineers really want to understand power flow, they don't track electrons, they track fields, where the energy actually goes. Let's be precise. Energy flows from the battery to the load, like a bulb or motor, not through the wire in the way people imagine, but through the space surrounding the wire. The wire guides the energy. It does not transport it like a pipe. This is why changing wire geometry matters. Insulation matters. Nearby conductors affect behavior. If energy were simply inside the copper, none of that would matter much. Why the speed of light fact confuses people. People often hear, electrical signals travel near the speed of light. Then they imagine electrons racing through the wire. But what's traveling at near light speed is the change in the electric field, not the electrons themselves. It's like this. When you pull one end of a rope, the wave travels fast, but the rope itself doesn't go anywhere. Electricity works the same way. Why intuition breaks down, and that's okay. Our brains evolved to throw rocks, not to understand fields that exist everywhere in space at once. So when electricity behaves in a way that feels unintuitive, that's not a failure of physics. It's a limitation of our instincts. Good physics doesn't try to protect intuition. It replaces it with better questions. Stop asking what is flowing. That question leads you into trouble. A better set of questions is, what fields exist? How do they change? How does the system respond as a whole? Once you ask those questions, the confusion begins to disappear, not because things become simple, but because they become honest. The real mistake people make, the biggest mistake, is thinking electricity is a thing. It isn't. Electricity is a relationship between charges, fields, and energy spread across space and time. When you accept that, circuits stop feeling magical. They start feeling subtle. What you should take from this, if there's one lesson here, it's this. Nature doesn't care about the pictures you like. It only responds to the rules it follows. Electricity works not because electrons march obediently through wires, but because the universe allows fields to coordinate behavior across an entire system. That's not simple, but it's beautiful. Now that we've stopped pretending electricity is a little substance flowing through wires, we can finally talk sensibly about something everyone uses, but almost no one understands: resistance. People say, this wire resists the current, as if the wire were stubborn. But resistance is not an attitude. It's a consequence. What resistance is not? Resistance is not electrons getting tired. It is not energy being destroyed. It is not electricity slowing down because it meets obstacles. Those are pictures, not explanations. If you imagine electrons as balls bumping into atoms, you might think resistance is just traffic. That picture is partly useful, but it hides the real story, what resistance actually means. Resistance describes how much energy per unit charge is transferred from the electric field into random motion of atoms. That's it. No drama. The electric field pushes charges. The charges respond. The lattice of atoms resists that motion by constantly interrupting it. The energy doesn't vanish. It becomes thermal motion heat. Why electrons don't carry the heat away? Here's another common mistake. People imagine electrons picking up energy from the battery, traveling down the wire, and dumping it into a bulb. That's not what happens. The energy transfer occurs locally, everywhere along the conductor, as the field does work on charges, and that work is converted into heat. The electrons mostly stay near where they started. Again, fields do the work. Electrons répondent. Why heating happens everywhere, not just at the end. If energy were carried like a package, heating would occur only where the package is delivered. But wires heat along their length. That tells you energy is being transferred continuously, not delivered at a destination. The wire isn't a delivery route. It's a place where work is constantly being done. The misleading idea of energy loss. People say energy is lost as heat. Nothing is lost. Energy is transformed. Calling it loss only makes sense from the perspective of usefulness, not physics. From nature's point of view, everything is accounted for. Why resistance depends on material. Different materials resist differently because their atomic structures respond differently to electric fields. Some lattices allow charges to move with little disruption. Others interfere constantly. Temperature matters because atoms vibrate more when hot, increasing interruptions. This isn't friction in the usual sense. It's interaction. Why superconductors are so strange. Superconductors are interesting precisely because they break our expectations. They allow current to persist without resistance. This doesn't mean electrons move freely forever like bullets in space. It means the usual mechanisms that convert field energy into random motion are absent. The field still exists. The system still responds. But energy isn't dissipated as heat. That should tell you resistance is not inevitable, it's conditional. Why power is the real quantity to watch. Voltage and current are useful, but power tells the real story. Power is the rate at which energy is transferred. When something heats up, power is flowing into it. This again emphasizes that electricity is not about movement of stuff, but about rates of energy transfer. Why intuition keeps failing. We want electricity to behave like things we already understand. But electricity belongs to the category of things that don't sit still, don't live in one place, and don't fit into simple containers. It's a field phenomenon. Once you accept that, the confusion fades not because things become obvious, but because they stop pretending to be. The deeper lesson, resistance, heat, and energy conversion, teach us something important. Nature doesn't punish systems for moving charge. It simply responds according to structure and interaction. When energy turns into heat, nothing has gone wrong. The universe has just followed its rules. Now that we've gone through fields, circuits, resistance, and energy, it's worth asking a final question. Why does the misconception about electricity survive so stubbornly? The answer is not ignorance. It's convenience. Simple pictures work until they don't. The water flow analogy works well enough to get students through basic problems. It lets engineers calculate currents and voltages without talking about fields every time. It's efficient, and efficiency is seductive. But the price of efficiency is depth. Once a simple picture works, people stop questioning it. They stop asking whether it is true and settle for whether it is useful. That's how misconceptions become permanent. Physics is not about pictures, it's about consistency. Real understanding in physics doesn't come from having a vivid mental image. It comes from having a set of ideas that agree with experiment, don't contradict each other, and continue to work when pushed into new situations. Electricity feels strange because it refuses to sit still inside a single picture. It demands that we think in terms of relationships, not objects. Why fields feel uncomfortable? Fields are everywhere. They don't have edges. You can't point to one and say that's where it is. So people treat them as abstract. But the irony is that fields are more real than the pictures we replace them with. They carry energy. They exert forces. They determine motion. Ignoring them doesn't make electricity simpler, it makes it wrong. Why electrons get too much credit? Electrons are easy to blame and easy to imagine. So they become the heroes of the story. But in most circuits, electrons are background actors. Necessary, yes, but not decisive. The electric field is the director. What understanding actually feels like? Understanding electricity doesn't feel like certainty. It feels like comfort with uncertainty. You stop asking, what is electricity really? And start asking, what does it do? And how do we describe it accurately? That shift is maturity in physics. The final misconception, the biggest misconception about electricity is not about wires or electrons. It's the belief that understanding means having a tidy explanation. Nature is under no obligation to be tidy. It is only obligated to be consistent. Why this matters beyond electricity? This way of thinking applies everywhere. In science, in engineering, in learning. Whenever an explanation feels too neat, too familiar, too comfortable, that's the moment to slow down and look again. Because the truth often lives just beyond what feels intuitive. What to remember? Electricity is not a thing that flows. Energy is not carried like cargo. Wires do not contain power. Electricity is a coordinated behavior of fields, charges, and energy spread across space, responding as a whole. Once you accept that, the mystery doesn't disappear. It becomes clearer. The goal of physics is not to impress. It's not to sound clever. And it's not to eliminate wonder. The goal is to replace confusion with clarity without pretending the universe owes us simplicity. Electricity still isn't simple. But now, at least, it's honest.